Hi, our next speaker is Professor Prahladh Harsha from TFR. He'll be talking on decoding multivariate multiplicity codes on product sets. Prahladh, you can.
Thanks, Pranay. Thanks to all the organizers for a great day of talks. Another day to look forward. And thanks to all of you for staying this late. I know it's been a long day, so I'll try to keep the talk at a very low technical end. I'll try to more impress upon you the main questions that we talk about without getting into any proofs or anything. I won't be, actually, this will be free flowing. This one is actually the stream of consciousness talk. I haven't made slides. I made slides, rather I disposed them off, and I'm going to give it live talk. So this is going to be a very recent work with Siddharth, also from STCS, and two friends of the department, Mrinal Kumar and from IIT Bombay, and Madhusudan from Harvard. It's on decoding multivariate multiplicity codes on product sets. It has a very coding theoretic title, but I'll try to keep the jargon from coding theory as minimal, if not zero, as possible. We'll talk more about it as there'll be certain math about polynomials that we care about. And what we're interested is the algorithmic version of this math. Okay, let's get started. A basic maxim in a lot of applications of polynomials has been that distinct polynomials look very different. So once again, feel free to stop me at any point of time. This has been, many a complexity theorist has made a career out of just trying to understand the statement and ways. So what do I mean by this? So let's try to formalize this. Let's do it. Let's start off with a very simple case. Suppose F is some field. You can think of any field. You can think of the field of rationals, the reals, complexes, or some finite, say some finite field. Any of them. And let P, in one variable, be a univariate polynomial in this field. And so P is let's assume it's a non-zero univariate polynomial. Non-zero polynomial of degree at most D. We could ask, so if you, for example, if you're the rationals, you could plot this. For instance, you could plot this polynomial. So you have a polynomial that goes, say, okay? And we could ask us, how many times does this polynomial cut the x-axis? Cut the x-axis, the x-axis, yes, the x-axis. Basically, so I'm interested in this one. What is the number of A's in the field such that P of A is 0? And we know that this is at most, this can, as if P were non-zero, here it's important that P is non-zero. If P is non-zero, then the number of times it's going to cut the x-axis is at most till D. And this, it's not hard to prove this fact at all. Yes?
It's small d, right?
Did I put small d? Yeah, I've been using capital D, no?
Oh, no, but
the line above has a small d that you might want to change to capital D.
Yeah, sorry. I will use capital D throughout this one. And I'm just going to write this in a slightly more fancy this one, because we'll come to it this one. This is just, I'm going to write this as summation over all A in F of the indicator function that P of A is 0. This is at most D. But by the way, we should immediately ask us, why does this already tell us that, so this is a basic fact I'm going to be working with. Why does this tell us that two different polynomials are distinct, are very different? Suppose you have two different polynomials, P and Q. They are different. In particular, the difference between the two polynomials is not the identically zero polynomial. This says that if that were indeed the case, then P and Q are going to take the same value at most D times, at most capital D times. Otherwise, they look very different. So two low degree polynomials, if they are different, they look very different. They can be at most share D common points of evaluation. In the rest of the space, they completely disagree. So this sort of tells you this following nice, it's an immediate corollary of this fact is the following, this one. So let's take, suppose I give you, suppose you have a set S. S is some finite set of the field. So some finite set, and I give a function on S. I give you a function on S. Think of this function. I want to say then there exists at most one polynomial P of total degree less than this one, such that when I pick a random A from S, probability of A not equal to f of A is less than or equal to half 1 minus. So I want to say, suppose you I give you any function f, there can be at most one polynomial which has this feature. And what do I mean by this? Let's quickly see a proof of this fact given what we did in the past. It says, so let's look at this circle of radius. This is the radius I'm talking about, half into 1 minus d by mod s. Suppose there were two polynomials in this. That is, both these polynomials are not too far away from this function f. Then in particular, this would mean that these two polynomials from each other, they are at most 1 minus d by mod s far away from each other. But then that means they agree on too many places. So in particular, you have the fact that if you give me any function, there exists at most, and this is the key fact over here, there exists at most one polynomial which has this feature. In fact, for people familiar with coding theory, this forms the basis of the code called the Reed-Solomon code, but we'll not go into that. So given this one is the previous basic maxim gave us this fact that you give me any function, there can be at most two polynomials which are within this ball around this function. So once you see such a thing, okay, this is a very clean combinatorial or mathematic fact. Once there's at most one function, you can ask the question, can you algorithmically realize this theorem? So immediately you can ask, can you algorithmically realize this theorem? Realization of above fact. And what do I mean by that? I'm asking, now if I give, does there exist an algorithm that given a finite set yes and a function outputs the one polynomial if it exists that is close to this polynomial? And the answer to this is yes, we actually know how to do this. And the proof of it's a non-trivial proof. Yes, there are several responses. There's the Peterson algorithm. So Siddharth mentioned some of these in his talk. Peterson algorithm, there's the Berlekamp-Massey algorithm. And then there's a Welch-Berlekamp algorithm. And most of these, especially the Welch-Berlekamp algorithm, just uses plain linear algebra over the field. As long as you can do some linear algebraic operations over the field, you can solve this problem. So we'll assume that the field comes equipped with doing some basic linear algebra. You can solve linear systems, you can find inverses and stuff. If you can do this, then we can solve this particular problem over the field. So there's a basic fact which is written in orange here, and that's very easy to prove. What I'm asking in this one is, can you algorithmically do the same thing? Can you actually come up with an efficient algorithm that finds this polynomial? This is a non-trivial task, but we do know how to do this. And what we'll see in the rest of the talk in the remaining 10 minutes or so that I have, we'll see generalizations of this basic math fact also which are easy to prove, and then ask, are the corresponding algorithmic counterparts also easy? Okay. Any questions so far? Okay. So what are I'm going to think of, so this problem is what is called the unique decoding problem of Reed-Solomon codes. Let's ignore.
So Prahladh,
Yes.
I mean, some sort of a silly question. So one could ambitiously hope that I don't know if this makes sense, but any fact that is proved making an appeal to this fact, to this basic fact that two polynomials of degree at most d can only agree at most at d places. I mean, you could ask whether any such fact, I mean, well, here fact I'm not formally defining it, but any such, sort of search problem associated that can, whose existence is proven by this, whether you can algorithmize it.
You can ask that question in general, but what we'll see is actually even very basic things. Forget about, there are very profound, deep theorems that are based on this fact. You can ask if there are algorithmic or constructive versions of those theorems. We will see that actually even very basic questions, we don't yet have algorithmic versions of this. That's basically what I want to actually impress upon you. That is, there are very basic questions related to this fact for which we don't have algorithmic counterparts. And I'll present one such which our main result is an attempt to solve one such problem. Okay. So I'm going to look at some generalizations of this maxim. So in particular, what we showed was a non-zero degree d polynomial can be zero at most degree d places. We'll think of two sort of generalizations. One, the notion of multiplicities, and the other to multiple variables. Let's see the multiplicities, generalization to multiplicities first. So what was the basic maxim that we had? Let me just copy that here. Okay. So now I'm going to ask, suppose we had the same picture as before. P was some degree at most d polynomial. We'd ask how many times it crosses this one. We can sometimes look at it carefully. Sometimes it might not. It might touch the. So for instance, over here, though this is a zero, this point, though it's a zero, it's actually a zero with multiplicity 2. In particular, for all points, we can define the following concept. For any point in f, you can define the multiplicity of the polynomial p at the point A to be the minimum s such that p of A, p prime of A, all the way up to p to the s minus first derivative of A, all of them are 0. Ask this question. That's the number of times the point is going to be 0. And in fact, this theorem over here can be strengthened.
Prahladh, that is max.
This is max.
Yeah.
So strengthened to the fact that the multiplicity of P of A belongs to F is actually less than or equal to T. Not just one. Even if you count it with multiplicities, the statement is true. Okay. Now, once you give this fact, you can ask the following algorithmic question. For any finite set S, and suppose I give you a function f from S to f bar S. That is basically, I'm giving you function. Let me first write down the statement. There is at most one polynomial P of degree less than or equal to D, such that if I pick a random A in S, f of A is not equal to P of A, P prime of A, this vector, Ps minus 1 of A is less than or equal to half into 1 minus possibly equals, let's call this R. Let's usually call this one, let's call it R. And this is R times this. So almost the same statement, except that you have this fact that you give me a function which not only gives the value of the polynomial, but also its R derivatives. And now what you're asking is how many polynomials have have this feature? How many polynomials agree with F on most of the places, on more than half into 1 plus d over R mod S set of points F and P should agree on. This is just like the previous thing was the immediate corollary of the basic fact. This is a corollary of this enhanced fact, and this is easy to prove. This fact is also easy to prove, and so is this. So once again, we can ask the question: what is the algorithmic? Is this feasible algorithmically? To answer this question, this is another one. You can ask if this is feasible algorithmically, and it so happens that extensions of Welch-Berlekamp do work. So that's the multiplicity. Any questions so far? No. So what we'll now look at is yet another thing. Now we're going to sort of generalization of the maxim to higher dimensions. Higher dimensions, higher number of variables. As before, F is some field. P now is a total degree polynomial in the M variables. So M is the number of variables. S is some finite set F. We can ask this question: if you pick a random point A in S to the M, what is the probability that P of A is 0? Once again, P is non-zero. Notice in the case of the univariate setup, we had T by mod S was the answer to this, and the exacts and the same. The screen is not sharing. You see what's happening on the, yeah, I think it is. There's a big lag behind what I'm doing and what it is doing. Just give me a second. Sorry.
One thing you could do is try connecting to your mobile hotspot or something. I think the issue is with respect to the internet.
It has done. Yeah, okay. And this is what many of you would have seen. This is what is called, there are several names for this. It's called once the Schwarz-Zippel lemma, the polynomial identity lemma. The generalization of the basic fact to larger dimensions has been known for close to 70 years or so. It's a point of time. It's a very simple. It's very easy to prove this. It just follows from induction from the basic fact. You can prove this statement, the basic fact. So once again, you can now ask the question which I've asked and they've asked: is the algorithmic version of this true? In particular, you can ask the following question now, because this question is so given any S subset of F.
There is a lag, I think.
Lag. You suggest moving to this one?
Finally, the things have appeared.
Yeah, let me go ahead with this. I don't want to disturb it. So m the number of variables, and I give you f, some function from s to the m to f. Then there exists at most one polynomial p such that probability when you pick a random a s to the m, p of a is not equal to f of a, is less than half into 1 minus d by s. Okay. The same fact, and now you can ask, can I do this algorithmically? And strangely enough, this problem was not solved till very recently. We knew how to do this previously. We knew how to do this only for special cases of S. This statement is true for any S, but we knew how to do this only for special case of S. In particular, till it was solved as recently as solved by Kim and Koparty as recently as 2016. So till then, we actually did not have an algorithmic proof of this. That is, give me a function and you want to find the multivariate polynomial which is close enough to this, which is guaranteed by the Schwarz-Zippel lemma. You wanted an algorithmic counterpart to the Schwarz-Zippel lemma, and we did not know how to prove this till the Kim-Koparty result from 2016. Yeah, so we don't have algorithmic counterparts for all of this one. Even for something as basic as this one, we did not have an algorithmic counterpart till very recently. And it's a very delicate proof of Kim and Koparty.
Sure, thanks.
Okay, and so now what you're going to ask a question, and the question which I want to now pose is mix. So generalization to both multiplicities and higher dimensions and multiple dimensions. So recall the notion of multiple. So now I'm giving you a polynomial p in f less than or equal to d, x1 to xn. Recall the notion of multiplicity. The way we had defined it was the maximum s. For the univariate case, we had defined it as a maximum s such that all the derivatives vanish. Now you're not going to just say all the derivatives, you want derivative in every direction to vanish. So you want to say that for all I less than s, dou p of dou x to the e at the point x equals a should be 0. For all monomials x to the e, this might seem like a very degree x less than or equal to pi. It's exactly the same definition. It might seem symbolically very this one, but just it's exactly the number of times, number of derivatives. You want that every derivative of size at most, order at most s to vanish at this point, and that's what you call the multiplicity of the polynomial at this point. And the multiplicity Schwarz-Zippel lemma follows easily from induction. In the same way, it states that for all finite sets S, subset of field M capital D, and P is a non-zero polynomial. polynomial of degree less than or equal to d, we have the multiplicity of PA as you range A from S to the M, 1 over just will be less than or equal to D by less than or equal to D. Let me write it this. Less than or equal to D times S to the power M minus 1 by no, sorry, just that. That's the multiplicity Schwarzschild lemma. And so now you can ask, does this have an algorithmic counterpart? In particular, let's go back to the same question. So suppose given, so for any function f from S to the M to F to the power M plus R minus 1 M. What is this? This is, so I'm giving you the function. So for every point A, I'm giving you the value of the function and all derivatives up to order R. Up to order R. Question is, there exists at most one polynomial P of degree less than or equal to D such that the derivatives of dou P by dou XC for all degree XC, the set of derivatives less than R, this is not equal to F at A. This is less than or equal to half into 1 minus D by R plus. This is just a consequence of the multiplicity Schwarzschild. And our main result is going to ask, can I do this algorithmically? Can you find this one polynomial? And strangely, this is open, and what we do know, so our result states that if under some, yes, under some caveats, one, the characteristic of the field should be at least the degree, or the characteristic should be 0. 2, the multiplicity parameter R is large enough then can algorithmically decode. And we don't know if these conditions are necessary. For the multiplicity Schwarzschild lemma says that irrespective of these conditions, they always exist a unique polynomial. What I ask now is to find that unique polynomial algorithmically. We don't know how to do this in general, but under these specific conditions, you can do this. In particular, even for this very specific, the multiplicity Schwarzschild lemma, which has found a lot of applications in recent years, we don't yet have a full-fledged algorithmic counterpart for this statement. I think this is a very interesting algorithmic question about such a basic fact about polynomials, which we don't yet know. We're just asking, this basic fact tells you there's at most one polynomial, find this polynomial for me in an efficient fashion. We know how to do it in several special cases. For example, it's rather strange, that is, the multiplicity parameter R proof works only when R is large enough. When the multiplicity parameter is 1, the Kim-Kopati results gives it to you. But then, even at 2 we do not know how to do. Once you go sufficiently large enough, then our result sets in and we are able to do. So we believe it should be true everywhere, but I don't know how to prove this. I don't know how to give such an algorithm. I will stop with this. Last answer questions. Yeah.
So, any questions?
Here, if s raised to m, is all you need about s raised to m is that it has this sort of permutation invariance, or can you take sets that are not product sets but have this permutation invariance?
No, so the multiplicity Schwarzschild lemma holds good for any product sets, and the product sets don't have to be the same. It could be S1 cross S2 cross SM.
I see.
I could work with that. They needn't have. It doesn't have. It just has to have a product structure. It doesn't have to have the same yes. I don't think you can correlate it. I do not know the version of the multiplicity Schwarzschild lemma if the points are correlated. That is, in each dimension, each variable, it should be independent.
I see.
Yeah.
Thanks.
And just to come up in this place where we actually manage to decode, we not only uniquely decode, we also actually list decode all the way up to capacity. Or this one, that is, we can decode all the way up to the distance, not just half the distance. But where we don't know, we do not know anything. We don't even know how to do unique decoding. Where we do know, we know how to decode all the way up to capacity. As also mentioned, Kim-Koparty manage only to do unique decoding. They do not know how to push it all the way beyond unique decoding. So even for the basic, what's this called, the Reed-Muller decoding, Kim-Koparty managed to give an algorithm which solves in the unique decoding case, but we do not know how to do this in the list decoding problem for general product sets.
General product sets, the SI have to have the same size, or there is like minimum SI in the denominator or something?
You can put the minimum SI in this denominator, yes. Okay.
More questions? Not then it's time for Prahladh.